Welcome back. Today we are going to talk about another model which is called K-Omega model. To recap what we have learned in the K-Epsilon model, one of the drawback of K-Epsilon model was that close to the wall we should have a y plus value from 30 to 100 because epsilon goes to infinity as y distance from the wall goes to 0. Even though K epsilon solves two extra variable, which is the turbulent kinetic energy and the turbulent dissipation, it still is not good close to the wall, and we have to use wall functions to resolve viscous sublayer and up to the log layer. Therefore, we needed a model which solves for both dissipation and kinetic energy and resolves well close to the wall. Therefore, this model came, which is called K omega model. In addition to this transport of turbulent kinetic energy, which is this, instead of the epsilon term, the dissipation, we have the omega. So what is omega? Omega is specific dissipation rate. Omega is given by epsilon over beta star times k, where beta star is the model constant. Notice that as epsilon goes to 0, k also goes to 0 close to wall, and omega resolves well. Therefore, this value resolves well close to the wall. For omega, we have a similar transport equation, which is when we solve these two together, we are essentially using the K omega model. The turbulent viscosity is estimated using K over omega. Notice the difference we had for K epsilon, we had C nu K square over epsilon. Let's see how we can calculate K and omega. For K, the calculation is same. So K is calculated as 3 over 2 u times I whole square, and omega is calculated using a similar formula as we have seen for epsilon, which is this, where L is the turbulent length scale, which is 0.07 times the hydraulic diameter. For wall, this one is for inlet slash outlet, and for wall, K is set equal to 0 and omega is set 6 nu times beta 1 y square, where y is the first cell distance from the wall and nu is the kinematic viscosity, and beta is equal to 0.075. So let's first calculate all these values for our case. K we have already calculated. Anyway, let's calculate that again. K is 3 over 2, u is 0.54 times I is 0.05, this whole thing whole squared times 1.5, and this is equal to 0.0010935, and then taking the square root of this and then divide by 0.09 to the power 1 by 4, and then divided by, this is equal to 0.07 times h. So h is 1, 0.07 is, we have to put 0.07 directly, 0.07, and we get omega is 0.8624. And now let's calculate the value close to the wall. Close to the wall, we had a y plus of approximately equal to 1. The y value was 0.0005. Let's calculate according to this. New value is 6 times 1.5 e minus 5 divided by 0.075 divided by y squared, which is 0.005 whole squared. This value should be equal to 4800. So we are going to use these values for our K omega model. Now, before going to the simulation, let's talk about a blend of K omega and K epsilon and why do we need it. Close to the wall, this K omega model works perfectly fine. But when we go away from the wall in the free shear zone, then this K omega model does not perform so well because this omega is very sensitive. Therefore, in order to prevent this, a blend of K omega and K epsilon was proposed, which is called K omega SST model. In this model, the turbulent viscosity is evaluated by this particular formula, which is max of A1 times omega times SF2, where S is the invariant measure of the strain rate tensor and F2 is a blending function. Blending function makes sure that when we are changing a model from K omega to K epsilon, then the transition is smooth. We have two blending functions. This is F2 here, and we also have a F1 blending function which comes in the transport equation for omega. There is slight change in the transport equation of the omega property, which is this, plus this particular term, which is 1 minus F1 times omega 2 over omega, the inner product of the gradient of the kinetic energy and omega. Everything else remains same. The K and omega remains the same at the boundary, but we have this particular blending of K omega and K epsilon model with the help of this term. One of the question is, do we need wall functions? So remember, in K epsilon model, we were not able to resolve the viscous sublayer and up to this, which is the log layer. Since we were not able to resolve the flow up to these layers, we used wall functions. But in K omega model, we essentially do not require wall function because we can in principle resolve up to the viscous sublayer. But for this, the y plus should be less than 1. And in our case, we have a y value which is close to 1, but it is not less than 1. Therefore, we should use wall function. So there are two cases. If we resolve up to this, that kind of simulation is called low RE simulation. So it does not matter what is the actual Reynolds number, but if we are resolving up to this, these are called low RE simulation. And in case of high Reynolds number simulations, we do not resolve up to this. We can resolve up to around y plus 5 and use wall function. Let's go back to our simulation and solve using these two turbulence models, which is K omega model and K omega SST model, and see the behavior of the simulation. Do we get what we are expecting, which is a good reattachment length? Thank you. See you in the next lecture.